Hello again. We are back with our continuity. We're going to talk about a couple different types of discontinuity, though we have seen these before too. So they're going to be relatively quick. The three I'm going to talk about are jump, removable, and essential. At most, I would expect you to be able to identify these by their picture, like by looking at the graph and maybe say the name. However, I'm not expecting you to do a ton with them. So jump discontinuity is going to look something like this, where you have a function and then it literally jumps up and looks a little different. Often, this is going to happen from piecewise functions. And we'll see more of that later. A removable discontinuity would be otherwise known as a hole. So I'll draw two different examples. Something where there's a hole and it's actually filled in somewhere else, but a removable discontinuity does not necessarily have to be filled in anywhere, so it could look like this. Again, these are holes. We've seen those before. And then last but not least, essential. Essential has two different components. There is something known as an oscillating, I spelled it correctly, oscillating, and there is also infinite. So we have seen infinite before. We'll go straight to that one first. That would be on our asymptotes, basically. An infinite discontinuity right here is this asymptote, where there is a break. An oscillating discontinuity is going to be basically when the function goes like crazy. It literally looks like this. Maybe I will give you an example if you want to look at it on Desmos. I can't remember the problem right now, which function it looks like, but actually I'll pause and I'll show you real quick. All right, I just remembered that I cannot, using what I'm doing right now, switch my screen, but that's okay. So I went to Desmos anyway, and here is the graph of sine of 1 over x. You see that it has this oscillating discontinuity. Basically, if I kept zooming in here, which you can try if you want, it's just going to get deeper and deeper into this web of craziness. So that's what we got. I'm not going to ask you to take a limit here because the limit does not exist here. It keeps oscillating between these two values of 1 and -1 here. That's why we have this discontinuity. There's a break right here. All right, so these are three main kind that I would ask you to identify or maybe draw at some point. Now we got a problem. Pretty much the rest of this lesson is going to be different problems based around this idea. We are going to be asked a bunch of information about the following function. So given the function f of x is equal to x cubed minus 7x minus 6 all over x squared minus 9, we're going to do this in three pieces. We're going to start with the domain. All right, domain of a rational function. I know my denominator cannot be equal to 0. So I'm going to take that denominator, x squared minus 9, and I'm going to say it cannot be equal to 0. You can do this in two ways. You can either factor, see that it's the difference of squares, x plus 3, x minus 3 cannot be equal to 0, and then x cannot be equal to positive or negative 3. You could have also gone from here, said x squared cannot be equal to 9, then take the square root, x cannot be equal to plus or minus 3. It doesn't matter how you got it, but our domain is anything except positive or negative 3. How would we write this? Think about it, pause the video. All right, we got from negative infinity to negative 3, from negative 3 to positive 3, and then positive 3 to positive infinity. I am including everything except those values of 3 and negative 3. So that's our domain. Now, what would this function look like? I don't know exactly, but I do know because it is a ratio of polynomials, it is one of those rational functions. So it's going to have horizontal asymptotes, it's going to have vertical asymptotes. Right now, if you don't remember this, maybe flip back in your notes. How do I find vertical asymptotes? How do I find horizontal? I will talk you through it to some extent, but there is going to be a little review you need to do. So the question is this function continuous? Well, first let's consider, does it have any discontinuities? And then we can decide if it's okay. Any discontinuities? The two main ones we saw, and I'm going to go back, are jumps removable, so jumps, they've got to jump, removable holes. Hey, we know how to find holes. And then infinite was these asymptotes. We know how to find asymptotes. So now we need to ask ourselves, are there any holes? Are there any vertical asymptotes? We'll start with the hole. If you remember, we had a hole at places where our numerator and our denominator share a factor. I'm sorry, my handwriting is terrible. Okay, holes are going to be places where the numerator and denominator share a factor, which means I have to take this function, f of x is equal to x cubed minus 7x minus 6 over x squared minus 9, and I want to factor it. Well, I factor the bottom really easily, right? X plus 3, x minus 3. However, the top is not quite as nice. X cubed minus 7x minus 6. But if I know that I need to find a hole, or that's what I'm looking for, I'm guessing that the numerator will have either this factor or that factor. Both of those are really good places to start. Because we are in an online format, I'm just going to tell you the answer right now. It's probably easier, but if you want, try them both. Specifically, one that might be really good would be to do your synthetic division with the numerator, 1, 0, negative 7, negative 6, and use the 0 of 3. So that would be the factor, x minus 3 equals 0. Move over, get x equals 3. Try this. I pulled down the 1. 1 times 3 is 3. 0 plus 3 is 3. 3 times 3 is 9. Negative 7 plus 9 is a positive 2. Positive 2 times 3 is 6. And I get 0. What does this actually mean? Well, it means that I've factored my numerator to some extent. Specifically, dragging this down, I actually have in my numerator x minus 3 times this, which is really x squared plus 3x plus 2 all over x minus 3, x plus 3. And actually, let's go one step further and keep factoring this numerator. This is now easy to factor. Hopefully you're looking at that thinking, oh yeah, I know this is x minus 3 times x plus 2 times x plus 1 all over x minus 3 times x plus 3. All right, now we got to ask ourselves again, why were we doing this? Our goal was to find any holes or shared factors. Well, what do we have as a shared factor? X equals negative 3. So what does that mean? There is a hole at x equals 3. I can also then consider these to be canceled, right? I can cancel these factors. That's why the hole actually exists. Well, that means that I have, I'm going to drag this down, this is a removable discontinuity at x equals 3. Good to note. Then the second question is, do I have any vertical asymptotes? How do we find vertical asymptotes? Well, we look at the zeros of our denominator. In this case, the only 0 I have left is x is equal to 3. Excuse me. x plus 3 is equal to 0, which would be a vertical asymptote at x equals -3. So we have an infinite, otherwise known as essential, discontinuity at x equals -3. Why again? Because it's a vertical asymptote. Now let's put it all together, because unfortunately, we haven't even really answered the question at hand. The original question was, is this function continuous? And remember, a function is continuous if it is continuous on its domain. So what do we know about this graph? I know that it's a rational function. I know it has those smooth curves. I also know, because we just figured it out, that it has a hole, a removable discontinuity at x equals 3. It has an infinite discontinuity, a vertical asymptote at x equals -3, which means, is this function continuous? Yes. On every value other than those values that we said we couldn't have, positive or -3, it's continuous on everything in our domain. This is a continuous function with discontinuities. Why again? Because it is continuous on all three of these intervals. At -3, there is a vertical asymptote. At 3, there is a hole, but that is okay. The last question then is, how should this function be defined at x equals 3 to remove this discontinuity? So now we got to think about what they're actually asking us. I'm going to cross these out for a moment, just because we don't need to focus on them. We really need to think about this. How should this function be defined to remove the discontinuity? Think of this as we want to fill the hole. So here's what I know about this graph. I know that at x equals 3, there is a hole. So without giving a lot of detail, I know something, let's say 1, 2, this is 3, there's a hole right here. Okay, and I need to fill that hole. I need to find this y value so that I can actually say, here, it's actually closed up. How am I going to do this? By finding a limit. Because if I can find the actual limit here, what is happening as I get close to 3, that's going to be what I've plugged that hole in with. So it's not that bad, because we've actually done all the hard work. I want to find the limit as x approaches 3, y 3, because that's what we're trying to remove, of my original function. In this case, I'm going to keep that factored version. We already did the work. It's going to make it a lot easier. X minus 3, x plus 3. I'm also going to start right off the bat by canceling that hole. Otherwise, I would get 0 over 0. I can then plug in 3. So I have 3 plus 2 over 3 plus 1. Or excuse me, times 3 plus 1 over 3 plus 3. So I actually have 3 plus 2 is 5, 3 plus 1 is 4, all over 3 plus 3 is 6, or I have 20 over 6, or I have, well, I guess it's exactly 10/3. So what I am saying is, if I plug in 10/3 as this y value, I will plug that hole. Well then, what does it look like to actually fix this? I am going to create a new function g of x. G of x is going to be a piecewise function. It's going to be 2 parts. I'm going to be the original function, the x cubed minus 7x minus 6 all over x squared minus 9. I'm going to be that if x is not equal to 3. Basically what I'm saying is I want to look like my original function everywhere except the place we are trying to fill. And I'm going to be 10/3 if x is equal to 3. This is how I am fixing that hole. This then is my solution for that third question. I now have plugged up that hole. I'm going to show you a picture in a moment. All right, so again, I can't show you Desmos quite as easily, but I graphed my original function, and if you notice, this point is undefined. It is a hole. Also, look, here's our vertical asymptote at x equals -3. Then also notice, to plug up that hole, we are going to plug in the point 3 10/3. That's what this is saying. And notice, I get this nice little blue dot right there. I will go back and erase that so you can see that it actually exists. We are going to stop here for today. I will finish the other examples tomorrow.